Good day, I'm Norman Wobbeger. In this video we're going to look at quadratic and cubic equations. We're going to look at the classical formulas for both of those, and then we're going to have a look at how Newton's method, involving tangent lines and successive approximations, tackles general cubics and quadratics. So along the way we'll touch base with, of course, the standard, very familiar quadratic formula, but also a much less well-known formula, but still of very great importance historically, the formula of Tartaglia, Del Ferro, and Cardano for the general cubic. All right, let's start with the quadratic equation, which of course is very familiar, and we've already talked about that in Math Foundations 48. So let me remind you that if we have an equation ax squared plus bx plus c equals 0, and a is not equal to 0, then that's a quadratic equation. And if we want to solve for x, we don't know what x might be, then here's the standard manipulations that yield the classical formula. And this process is called completing the square. So we bring this c to the other side, we take out a factor of a, so there's a b over a here as the coefficient of x. And then we might as well divide by a to get that on the other side, so we have a minus c over a on the other side. And then to this thing here we add a particular term, which is obtained by taking this coefficient here and dividing it by 2 and squaring it. And to keep the equation the same, we do that on both sides, so we add that term on both sides. Then this is a perfect square. This simplifies to b squared minus 4ac over 4a squared. So this thing squared equals this. And then the usual thing is to say, well, let's take a square root. So the square root of 4a squared is 2a. Then we have a minus b over 2a when we bring this part to the other side, and plus or minus the square root of this numerator here, which is b squared minus 4ac. That's the familiar formula that all high school students learn off by heart. Now this formula is in some sense a fake formula because of this square root here. The square root presents significant problems for us. First of all, sometimes what's inside here is negative number, and then the solution doesn't make sense unless we first establish the more general theory of complex numbers. But historically, for many years, that was not available, and so people would have just said, well, there's no solution in that case. But even if this is positive, it still might not be a square. For example, this might be 2 inside here, and then we're talking about something like the square root of 2 involved with these other numbers. And since square root of 2 is problematic, so is this kind of expression here. If we go back one step to this one here, then it's possible to rewrite things in a somewhat more honest, logical way. What happens really is that this side being a square, this must also be a square in order for there to be a solution. Now the bottom is already a square because it's the square of 2a. So this really only has a solution when b squared minus 4ac is a square. That way the left-hand side and the right-hand side are both squares and things make sense. So this only has a solution if b squared minus 4ac is a square. In other words, of the form r squared for some number r. And whenever I say number in this context, we're talking about rational numbers. Okay, now if b squared minus 4ac equals r squared, then when we proceed in the same way as we did to get the formula, then what's inside here will be an r squared. And what we're really talking about is plus or minus r. In that case, the square root of r squared does make sense. We're really just talking about r. So the formula becomes x equals this, or more simply, minus b plus or minus r over 2a. This is more of a true formula, and I wish high school students were taught the quadratic formula this way. So if you're teaching high school, this is what you should tell your students. You have an equation like this. It has a solution precisely when b squared minus 4ac is a square. Then there's a solution. And if that b squared minus 4ac is r squared, then the two solutions are minus b plus or minus r over 2a. If b squared minus 4ac is not a square, then there is no exact solution. But there still might be approximate solutions. So as long as this thing is positive, we can find numbers r which maybe don't square exactly to this number, but which approximately do. And so that's the interpretation of the formula in that case. It's minus b plus or minus an approximate square root to b squared minus 4ac over 2a. If we interpret this to mean a number which has the property that if you square it, you approximately get b squared minus 4ac, then it makes reasonable sense. Many centuries ago, when European mathematicians were starting to flex their mathematical muscles, it was a common practice to offer challenges to your fellow mathematicians, often arithmetical challenges, to see if they could solve them. A quadratic equation would have been pretty simple because quadratic equations, well, they've been solved back in the time of the ancient Chinese, the ancient Indians, the Arabs. They all knew how to solve quadratic equations. They all had some version of the quadratic formula. But nevertheless, let's illustrate the point by cooking up a quadratic equation that we might be able to challenge somebody with if they didn't know the quadratic formula. For example, we could take a number, say 63, somewhat randomly. And let's take an expression which is quadratic in x. Let's take x squared minus, say randomly, 38 times x. You could compute that. 63 squared minus 38 times 63. Work that out. That turns out to be 1,575. So we know that x equals 63 satisfies this quadratic equation. Now this particular quadratic equation, we know it has an integer solution because we've cooked it up to have an integer solution. What would happen if we applied the standard quadratic formula on it? Well, there's the minus 38 with a minus sign becomes 38 plus or minus the square root of 38 squared minus 4 times this. So altogether plus 4 times 1,575. And what's inside the square root becomes 7,744. Now it turns out that 7,744 is a perfect square. In fact, it sort of has to be because we know we have to get an integer solution out of this. So this had better be something that actually is an integer. In fact, the square root is exactly 88, so the two solutions are 38 plus or minus 88 over 2. One of those you get with a plus sign gives you 63. The other one with the minus sign gives you minus 25. So those are the two solutions. So in this case, the square root of 7,744 has a proper meaning, since 7,744 is a square. But if we change this just a little bit, if we changed it to one less or one more, well then this no longer would have a solution. So if we changed any of these numbers just a little bit, then almost surely the equation that we would get would have a dramatically different nature. It would have a dramatically different nature, and this, what's under here, would not be a perfect square, and we would not be able to solve that exactly. It's like a night and day different type of situation. We would then only be able to find a square root approximately using essentially Newton's method or something equivalent, say the Vedic algorithm. Now I want to use this problem of solving a quadratic equation to illustrate that Newton's method, as I've explained it so far, is capable of some interesting generalizations. So we're going to generalize it just a little bit right now. Let's consider this particular equation. X squared equals 4 minus x. So that's a quadratic equation. And in the form that it's written here, we have a left-hand side and a right-hand side, so we don't have everything on one side like we did for the other quadratic equation. This suggests that there's some geometry here that's represented by one curve here and one curve here. And in fact, it's possible to interpret this equation as trying to find the intersection of two curves. One of them x squared and the other one the line 4 minus x. In terms of polynomials or polynumbers, we're talking about p equals alpha squared, say, and q equals 4 minus alpha. Now, this line here, this green one, is not a horizontal line like we've been considering before. But nevertheless, Newton's method works still quite well on it. So let me just run by that and show you how that goes. I remind you, this is the formula for the tangent line to the conic y equals x squared at a point r somewhere. So if r is, say, this one right here, then the corresponding point on the conic is that one there, and the tangent line to the conic at that point is given by this polynomial. And I'm using alpha here almost interchangeably with x. So if we want to find out where this tangent line meets this green line, we're talking about where this tangent line meets the line 4 minus x. And it will do so at some point whose coordinates are alpha, 4 minus alpha. Where alpha is the solution to this equation here, where we just set the equation of the tangent equal to the equation of the line. So we're looking to see which alpha or x value makes this equation satisfied. That's finding that intersection. Well, we can bring the alphas to one side and everything else to the other side. So 4 plus r squared on that side. And then on the alphas over here, we'd have alpha times 1 plus 2r. So when we divide by that, we get alpha equals 4 plus r squared over 1 plus 2r. And that gives us a new value of r, let's say r prime. So this is a way of successively finding approximations using Newton's method. It's very similar as to what we've been doing before, except that now we're looking to see where it meets some more general line. So there will be the first approximation, let's say R1. Then you compute this thing here, and then you get second value R2, maybe up there. And then the next level, we would look to see what the tangent line at that point is, right here, and where it meets the green line, and continue. So here's one case of a sequence of such approximate values where we start with R1 equals 1. So if R1 equals 1, then at the next stage, if we plug R equals 1 in here, we're going to get 5 over 3. And then at the next stage, when we plug 5 over 3 in there, we're going to get 61 over 39, and then 9,805 over 6,279, and then this number here. And we can keep going. And these R values that we're getting are getting closer and closer to satisfying this equation, although we never actually get a number which satisfies this equation. So what do we get when we apply the quadratic formula? Well, we can bring everything to one side, first of all, to get x squared plus x minus 4 equals 0. And then the solution is minus this coefficient here, which is 1, minus 1, plus or minus r over 2, where r squared equals b squared minus 4ac. 1 plus 4 times 4, or 17. So that's the solution to the quadratic equation that I would like to see high school students start writing. This is a logically clear and correct statement. Okay, so there's a solution as long as you can solve this equation r squared equals 17. If you can solve that equation, then you get a solution. If you can't solve that equation, you're not going to get a solution. If you can solve this equation approximately, then you get an approximate solution. If you can't even solve this approximately, you can't even get an approximate solution to that quadratic. Okay, so 17 is not a square, so there is no exact solution. But 17 is positive, so approximate square roots of 17 exist. For example, if you take your calculator and you ask it what is square root of 17, it will give you an approximate square root. Say 4.123106. Then it stops. So we can plug that into here, and then we get two solutions. X equals minus 2.12 1.561553 or x equals 1.561553. And we have to recognize that those are not exact solutions of this quadratic. They are approximate solutions because we're starting with an approximate square root of 17. Now, it's also possible to use Newton's method directly on this quadratic, of course. That means we could think about plotting this function, the function x squared plus x minus 4, or better yet, the polynomial alpha squared plus alpha minus 4. So here's my rather crude attempt at graphing it. I've plotted a few points and joined the dots. And now what we're doing is we're trying to find where this graph meets the x-axis. Value there, or perhaps a value there. So as an exercise, you can try to use Newton's method directly on this quadratic to find the approximate zeros. And of course, you should end up with something that's pretty close to those values there. These are the values that we're finding, approximately. So now let's have a look at cubic equations, which is an interesting chapter of mathematics and started really a whole important trend in algebra. Even though the actual cubic equation that I'm just about to show you turned out to be something of a dead end. It didn't actually lead to the breakthroughs that its discoverers had hoped. So, what's going on here? Well, we're talking about a general cubic equation. Say x cubed plus ax squared plus bx plus c equals 0. Now you might say, well, this is not quite general because I don't have an arbitrary coefficient of x cubed, and that's quite correct. So what I've done is I've divided by that arbitrary coefficient, which is non-zero, just to simplify the formula so there are fewer coefficients around. So the question is, how do we write down a formula for this that allows us to find solutions if we're given a particular cubic equation? In other words, we know exact values for a, b, and c. How do you find some formula for x, which will involve a, b, and c? Alright, so this problem was solved in the 1500s by, well, a combination of a number of people. Italians Del Ferro, Tartaglia, and Cardano. And there was quite a lot of dispute of priority and sort of interesting characters here. And this story is told a little bit in my Math History 6 lecture. So here, roughly, is what ends up happening. We first make a simplifying substitution to simplify the equation. If you replace x with y minus a over 3, and this a is exactly this coefficient of x squared here, divided by 3, then it turns out that you plug that in and you expand using the binomial formula and you collect terms, that there is then no more y squared term. So you get a formula that only involves y cubes, y, and a constant term. So we can rewrite it by bringing the other stuff to the other side as y cubed equals p times y plus q. And p and q are numbers that are related in a reasonably decent way to a, b, and c. So once we have a solution to this, then we can get a solution to the original equation through this substitution here. Okay, so then there's a very clever kind of trick that was discovered, well, maybe it was discovered by Del Ferro, but certainly by Tartaglia. And then he revealed it to Cardano, who then published it. And the trick ends up allowing you to write down a formula like this. And this is the cubic formula. So let's have a look at it. It's telling us what y is in terms of this number p and this number q. So there's a cubed root of q over 2. So this constant term divided by 2, plus a square root. And what's inside the square root is the difference between q over 2 all squared and p over 3 all cubed. So the 2 in the denominator goes with the 2 in the exponent there. This 3 in the denominator goes with that 3 in the exponent. So we have to take all of that, and then we take the cubed root of that. And then there's another term which is just like that, except that there's a minus sign here between these two terms instead of a plus sign. So if we know q and we know p, and we're good at taking square roots and cubed roots, well, then we can write an expression down for y. And if I call the quadratic formula something of a fake formula, well, this one is also going to be a fake formula, because we've just said it involves square roots and cube roots, and in general those things don't exist. Unless you choose things very carefully, the numbers that are inside here are not going to be perfect squares, and then the numbers that you get inside here are not going to be perfect cubes. So necessarily this is really only a way of getting towards some kind of approximate solution. Unless, of course, we work in some extension field. We take an algebraic point of view, which is always another option, but that's a little bit more advanced. So the usual interpretation is we're talking about ordinary numbers on the ordinary line. And unfortunately, what we get here generally is non-existent. Let's have a look at an example. So here's an example to see how this cubic formula works. We're going to cook up, first of all, a cubic equation whose solution we know. So we're going to start with the solution. Let's say randomly x equals 47. And then we're going to just cook up a cubic equation that 47 satisfies. So I'm going to randomly compute x cubed minus 36 times x squared minus 405x. And I chose those numbers more or less at random. And I compute that with x equals 47, and I get 5,264. So now I can give you this equation and say, what is x? Can you figure out what x is? This is the kind of thing that those 16th century mathematicians like to do, like to challenge each other with problems like this. Well, we saw that the first thing that one does is to try to make a simplification, so that instead of having 3 numbers involved, there are really only 2 numbers involved. And the simplification is x equals y plus 12. Why 12? Because it's 1/3 of, or minus 1/3 of this 36 here. So 36 over 3 with a minus sign, there's a 12. So when we plug x equals y plus 12 into here, expand it all out, then that can be rewritten as y cubed equals 837y plus 13,580. The numbers get a little bit bigger. It's the price you pay for having made some simplification, having no quadratic term. So now we're just in the position where we can apply that previous formula. This is the p and this is the q. So we have a cubed root of, here is q over 2, and here is q over 2 squared minus p over 3 cubed. And then the same kind of term, but with a minus sign here. So one can work out what this is. This is something squared minus something cubed, so we make the arithmetic. And then we look at that number and say, well, can we find its square root? Well, we can certainly pull out some quadratic factors. So we can write this as 473 times square root of 109. And so then we have the cubed root of 6,790 plus 473 times the square root of 109, plus the cubed root of 6,790 minus 473 times the square root of 109. So that's the solution that the formula, the cubic formula, gives us. Now, it turns out that if you compute this with a calculator, which of course is just using approximate values for here, and then it will use approximate values for the cubed root, you get 35.000000, suggesting that the answer really is 35. In fact, we're not surprised by that, because we started with x equals 47, and if x is 47, then y has got to be 47 minus 12, which is 35. So in fact, 35 is an exact solution to this equation, and that's the number that's being obtained here. But you can see that something remarkable is happening. That this thing here doesn't obviously simplify easily. This thing here obviously doesn't simplify easily, but somehow miraculously the sum of these two turns out to be 35. So there's some very subtle algebra going on here between these cubed roots and the nested square roots. And that to me is in fact the most surprising thing about this cubic formula, this interesting interplay that we get. In fact, the situation is even more complicated. In certain situations, what's inside these square roots here can be negative. And you may even have a honest, down-to-earth solution, but you have to go through complex numbers to get at it. So you have to widen your arena to complex numbers, even if you started off with a very explicit, perfectly reasonable integer value. Now this whole solution here depends very much on the fact that we started with an equation which we already know has a solution. If we change this 5,264 to something randomly close, say 5,262, well then you can go through the same motions and you get the cubic formula spitting this out. Cube root of 6,789 plus 93 times the square root of 2,818, and plus the cubed root of the same thing minus 93 times square root of 2,818. But the difference between this expression and this expression is like the difference between night and day. Here there is an exact value that this actually can be interpreted as. How, maybe not so clear, but it can't ultimately be given a concrete interpretation. But here the solution is only obtainable numerically, approximately. So we don't actually get this number. This is some kind of optical illusion here, presenting it as if it's already there on a plate. It's not on a plate. This is just a recipe for a procedure that you can carry on. And you can churn out as many digits as you have patience with and technology for, but ultimately you're never going to be able to get the whole thing. Let's have a look at how Newton's method would tackle that same cubic equation. So here's that same equation. I've rewritten it with x's instead of y's to make it a little bit more familiar. So x cubed equals 837 times x plus 13,580. All right, this is not an accurate picture of this, but one interpretation of this is to say, all right, we have two curves here. On the left-hand side, we have the familiar x cubed curve. Looks something like this. And on the right-hand side, we have a linear equation. In other words, a line. So in terms of polynumbers, alpha cubed on this side, and over here, 837 alpha plus 13,580, which is a line, maybe something like this, going through the y-coordinate 13,580 and having some positive slope so it increases. And our job is to find where this line meets our basic cubic x cubed. Okay, well, Newton's method allows us to tackle this kind of question. Even though, again, this is not a horizontal line as it was in our earlier attempts, still the basic idea works. We can still make an approximation, start with some approximate value r here, look at the point on the curve, compute the tangent, and then see where that tangent line meets this green line. And then drop down, that's going to be your new approximate value. And then you carry on, you iterate starting with that new value. And hopefully these values R1, R2, R3, and so on will more and more approximate a solution. So I remind you that the formula for the tangent line to the polynomial alpha cubed is, at the point R, minus 2r cubed plus 3r squared alpha. So that's a linear polynomial. That's the tangent line. And that will meet the line, this one here, at some point, say alpha equals r prime, where we get the alpha by solving this set equal to this. So there's the tangent line. We set it equal to the green line. We're trying to solve for alpha. Fortunately, alpha only appears linearly. That's because we have two lines. Intersection of two lines, it's always a linear equation. And we solve this in the obvious way. We get everything without alphas on one side, bring all the alphas to the other side. So we end up with 13,580 plus 2r cubed on this side. And then the coefficient of alpha was a 3r squared minus 837. And when we divide by that, we get the formula for alpha. So this is a way of going from r to the next approximation. Let's call it r prime. So you compute this expression with an r cubed in the numerator there, an r squared in the denominator there, and that steps you one step at a time towards finding a place where x cubed and this line meet. In other words, towards a solution of this cubic. So if we start with an initial guess of, say, r1 equals 30, then that recursion that we wrote down on the last sheet means that the next r2 will end up being this value here, 67,580 over 1,863. And then when you use this, plug it into the same formula, well, then the next value is this one here, which I won't read off. But I will tell you that it's approximately, in terms of your calculator, it's 35.056 and so on. So that means we're getting pretty close to 35. And if you iterate a few more, you're going to get closer and closer to 35. But in this case, Newton's method does not know that there is an exact solution. So Newton's method is not a method that will get an exact solution for you necessarily if it exists. Newton's method always just gives us a procedure, step by step by step, that gives us closer and closer and closer to a solution to whatever equation we're looking for. I'm spending a lot more time on Newton's method than a standard calculus course would, because I think it's particularly important application of the derivative, or better yet, the idea of tangent lines and tangent conics. It's also very important in practice, in the sense that this is an algorithm that computes solutions to equations for us, at least approximately. And so that's a main business of mathematics, in fact. But I'm also telling you about it in some detail because I want you to appreciate that Newton's method does not solve equations exactly. In fact, I want you to appreciate that in general, equations cannot be solved exactly. They can be if we cook up the equation specifically in order to have a solution. So yes, some equations do have exact solutions. But your average, ordinary, run-of-the-mill equation, if it's at all a little bit complicated, chances are you won't be able to solve it. Not exactly. But approximately, you can still have a good chance. I'd like to think about extending Newton's method to dealing with algebraic curves. Not just functions or polynomials where we have y equals some polynomial of x. But what happens if we have two algebraic curves? For example, a folium and a lemniscate, or maybe an ellipse, a second degree equation, a conic section. So here you can see this ellipse meets the lemniscate in 4 points, at least approximately. So we can ask, if we have an equation for that ellipse, if we have an equation for the lemniscate, how might we be able to find these values, at least approximately? Or same thing with the folium and the lemniscate, or the folium and the ellipse. At first it seems as if Newton's method is not going to work here, because Newton's method was involving having a kind of a functional approach, that we have a value of r on the x-axis, and then we go up. We compute the function's value at r, or the polynomial's value at r, because we've only been talking about polynomials, and then we look at the tangent line at that point. However, it is true that we can calculate tangent lines to these algebraic curves at any old point that we like. We know how to do that. So maybe we can still exploit the fact that we can compute tangent lines to somehow apply Newton's method or generalize Newton's method to this situation. So next time I'm going to talk about this, and I'm going to show you a way of thinking about the algebraic curves, about Newton's method, that generalizes it to this situation. It goes back to our earlier interpretation of what is an algebraic curve. You may remember I said that there were a number of different interpretations. There was sort of an interpretation A, where we thought of an algebraic curve like this as actually a picture, a set of points, or a curve in the plane. But then there was also interpretation B, where we thought of it rather in a bigger way as a sort of a slice of a surface. And there were some advantages to looking at things in terms of that interpretation B, and this will be a good application of that more general way of thinking, or at least higher dimensional way of thinking. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.